Also, I understand the need to discuss the technical aspects of a class and how things work and what can I do and can I still turn this in. I'd love it if we spend some time on the concepts themselves. It'd be amazing. Because that's the whole point of this, is to learn stuff. So, like me, going through college, I worked. I'm sure several of you worked several jobs. You have kids, whatever. Through college, I had 3 jobs. Right? I didn't do every homework assignment. I didn't make like A's but all I cared about was the fact that I understood what that stuff was. And maybe my grade was lower because I couldn't do every single homework assignment, but my focus was, do I understand the concept? And the focus seems to me of turning into, what can I do within this guy's rules to get myself to pass, instead of, what can I do to really understand what the concepts are in this class? And I know some of you guys are like tuning me out, but some of you guys are trying to do that. That's what you're supposed to do. And I live off of interact. I live off of questions. I just do. So if I'm not getting them, I go a little crazy. Because I'm like, if I were sitting out there taking this class for the first time, I have a lot of freaking questions about what the shit, how's that work? Why is that way? That kind of stuff. I'm really open to questions. I'm not sure if I've come off a different way or whatever, right? But I love questions about how stuff works. Okay. With that said, no pressure. Are there any questions from any homework that you guys are working on? You're all like, let me avert my eyes. Just another no. Because some of it's not, the book certainly has interesting ways to word things sometimes. Yes? Yeah. All right. So when you have this situation here, when you have when you have an x p of x kind of problem, how do you find the mean? Let's start there. We've got to build our way up to the standard deviation. How do you find the mean? What do I need to create to find the mean?
The multiplier.
Exactly, right? The equation for the mean. You multiply these and then you add them. You guys remember that? We talked about, we did this whole derivation of why this formula is true. I talked about the fact that the probability has an n on the bottom, so it's really the same formula as we had before. We had a worksheet that showed you how to actually do it in a calculator and get the next column and the next column. I'm not really sure what other way to do it. I could do claymation. Laugh it up, math boy. So yeah, you make another column to find the mean. You add these up. So it's basically, the way we look at it is the weight times the value. So I get a little too many people doing something like adding these up and dividing by 4. But can anyone quickly see why that doesn't make any sense, especially here? Will the average for this data be 1.5? Why won't it be? Who can tell me very quickly why it would not be based on what I've written? No, it's not. Right? It does add up to 1. I appreciate that, though. Please, dear God, keep an eye on me for addition. I have trouble sometimes. But that definitely adds up to 1. But what's the heaviest weighted data point? 3. So that's going to pull the average towards it. Another way to look at it is 40% of my data is 3s. 30% of my data is 2s. So if you add these up and divide by how many there are, you're assuming they're all equally weighted. You're assuming they all show up the same number of times, which is obviously not true. This multiplies a value by its weight. So who has more say in the average is the heavier weighted stuff. So I know now the average is going to be higher than 1.5. Oh, thank you. All right. So if I do this, let's kind of do this problem real quick. Multiply these out. If I add them up, I get the mean. So I get 0.2, 0.8, I'll get 2. Which is higher than the 1.5 that it would be if these were all the same amount of times. Yes?
This may be a dumb question, but if x times p of x and you add them all together is the mean, then what's the column p of x represent?
Yeah, what's p of x mean? There's 2 ways to look at it.
Data values.
No.
Sorry.
Percentage.
The percentage, so one way to look at it is, and this is the way we developed it. I developed it by having a list of 10 numbers and it had some showing up more than once. So if I had a list of 10 numbers, there would be 1 0, 2 1s, 3 2s, 4 3s. So 40% would be 3s, 20% would be 2.
So it's just giving us a value in like percentages?
So this is also could be seen as a probability.
Okay.
The probability that somebody has no pets. The probability somebody has 1 pet, whatever the situation is.
And then multiplying it.
Exactly. I love it. So again, we did a mathematical derivation, like the crazy people we are, of why this formula makes sense. I don't know if you guys remember that day. So you guys just wait for the formula, and then you forget why the formula works. Well, because you got to pay attention to where the derivation of it is. That explains why it works. Okay. So to get the standard deviation, we did some work on this too. What always has to show up in something related to a standard deviation is a term like this. Right? Because that's the heart of a standard deviation. It's the distance between a data point and the mean. So we started with this thing. I don't know if you guys remember. We multiplied each one of these by its weight. The same kind of reasoning behind doing this. We worked with that for a while, and we ended up with this formula for the variance. We didn't show every single step because this is not a class on summation algebra, which sounds painful, right? The algebra of summation. Oh God. These little symbols have a lot of algebra behind them. But if I do all the steps, you can at least see the first step, x squared p of x. Bam! And somehow the rest of it becomes mu squared. And I love how some of you just focus totally on, why doesn't he show us? Oh, screw it. It's little things about the summation symbol that we don't have time to get into in this class. But if I did work it out, FOIL it out, do everything, I would end up here. So this piece, what does it tell me? What column am I missing? Because what do I need to add up?
Multiply by column by.
Yeah, I need a column of x squared p of x's. I need a column of these, so I'm able to add these up. That's the way I've tried to say that formula. Wherever summation symbol shows up, that's the way to look at it. What do I need a column of? Whatever's after the summation symbol. Because how can you add them if you don't have them? So now I can multiply. So the way I told you to do it was L1 times L3. You could also do L1 squared times L2. Either way you do it, you get the same number, which happens a lot in math. Multiple ways to get the same answer. So if we do it here, it'd be 0, 0.2, 1.2, and 3.6. How we doing? We are. Everybody all right? So I love you guys. The reason this class is difficult is because it's concept married with formulas. Right? So on one level, the class is really easy if you kind of allow yourself to believe that. There's just a bunch of formulas, got to plug shit in. But that's when people start to put stuff here and put stuff here. I mean, that doesn't make any sense for the idea of what this symbol does. That's what I mean by concept married with formula. I need a column of these. So I got a column of those. So how do I figure out this piece? Add them up. So I get 1.4, I get 5. I add those up. So 5, that is the sum of x squared p of x. That is not the variance. That's not the standard deviation. That is just this piece of the formula. You got to put it in. I'm hoping this feels a little familiar because there's that whole handout we did. We had all these formulas, all that. Okay, I like it. So variance would be 5 minus 2 squared, which is 4. So I get the variance is 1. So I get the standard deviation is 1. That kicks ass. That's neat. I like that. I wish I could say I forced that to happen, but I have no idea. Just made shit up and ended up happening. So again, you might have been able to just gloss over when the teacher derived the formula before, but in statistics, that is a part of it. That helps you figure out when to use it, that helps you figure out how to interpret what the formula says, which is why I do it, right? Okay. So that definitely answers that question. So I did kind of have to add it in. For some reason, this book, they kind of do a little too much in the calculator. Some of you guys are like, no, they do the right one. No, they don't. They do too much. My opinion is the one that matters in that respect. But that's why I had to add that on to 76 and 77. That just means putting one more column on that sucker that you had to do already anyway. All right, how are we doing there? Okay, I like it. Okay, so anything else from homework stuff? Or yeah. Yeah.
And
5.1 number 6 and 9. Oh yeah, okay. All right. All right, so everybody's got what they want from this? Okay. Let me ask you this. We've looked at this kind of a distribution here, right? And it's called continuous because it doesn't leave out any values between two given values. It's continuous. Right, so does this value go somewhere? Yes, yay. What do we call this kind of distribution? Not just continuous, it's specifically uniform. I like it. There are other continuous distributions. You could have something like this. It's like an exponential distribution. It's just continuous. I don't care what kind of continuous thing it is. If this is 0 to 15, what's the probability that x is greater than 15? 0, exactly. So go with your gut there. The only possible values, the only things that could happen are 0 to 15. So if they ask you a probability, so a few questions will maybe seem silly, or you're like, I don't know how to do that, when really the answer is easy. It's outside the realm of what's possible, right? What's the probability that there's somebody who weighs negative 80 pounds? Well, ain't gonna happen. That'd be freaky, little black hole man. No, don't get too close to it. Is that cool? I mean, that was one of them. Oh, now here's the one that's a little freakier. What was the heart of any question I can ask here? I can ask, what's the probability that, how tall would this thing be? 1/15, I love it. So the overall, the area is 1. So now the visual corresponds directly to a probability distribution. All the probabilities add to 1. The total area is 1. So if I ask you what's the probability that 2 is less equal to x is less equal to 7, yeah, it's 5 wide. And how tall is it? 1/15. So it really is just the area of that rectangle. 5 times 1/15. So it'll be 1/3, 33.33. Now, what if I ask you this question? This is a little bit weird. What's probably that x is exactly 11? Now, if you think about it in the same way we just did that one, the answer is easy. What if I would have made this 2 to 6? What would have been different? The answer would have been a little smaller because the width would have been smaller. What if I made it 5? Smaller. 4, 3, 2. Would have made it 2 to 2. Well, how wide, or in this case 11? How wide is from 11 to 11? 0. It's got no width. A 1 width would be 11 to 12, wouldn't it? That would be a 1 width. 1/2 width would be 11 to 11.5. That's still valid. But any specific data point has a probability of 0. Now, just to blow your minds, and maybe a few of you guys will be interested in this, do you know what infinity is, right? It's nothing you can get to. If you do get to it, I think you would go to the next realm of consciousness or something. I always think about the movie Powder when he gets struck by lightning. If you've never seen it, boom, it just becomes energy. There's another idea that's the inverse of that, and that is the smallest positive number. And a lot of my math colleagues in the world, if you watch this, I don't give a shit. There's something called Iota. You might have heard of the word Iota before. Sort of related to it ain't gonna happen, right? The probability is so small, it's got an iota chance. So iota would be kind of like the smallest positive number. So if you think about it, how could each element of this have a probability of 0? Well, in one sense, it has to. If any single thing had a probability bigger than 0, and how many numbers are there between 0 and 15? Don't say 15, that'll make me very concerned. How many numbers are between 0 and 15? Infinite number of numbers. And if each of them had a non-zero probability, you would add them all up and get way more than 1, right? So in reality, each of them has iota. And basically, as a human, we just call it frickin' 0 just to get to the end, right? But you guys, I went a little bit further than that too, and I don't care. You can look up iota and see if anybody talks about it. Okay. So whenever they ask you a probability outside of this realm, it's impossible. Everything out here has got what height? 0. So it's probably anything out there happening? 0 chance. Right? And if they ask you probably of anything, any specific number happening, 0 chance. I like it. I like it a lot. Okay. And that's such a foreign concept, because if I said, what's probably you go and find a textbook that weighs exactly 5.2936666 pounds. It's basically 0. It's basically 0. Yeah, it's like iota. I love it. Correct usage. Little tear. Okay. Anything else from homework? Is that decent? 21? 41. Oh, yeah. There is one little thing that I kind of left for you to read about, because I'm not going to make a big deal out of this, but they tell you how to figure out the average and the standard deviation for a uniform probability of distribution. So I'm going to write this down once. I'm not even going to put this on your formula sheet, but there are going to be a few homework problems. Some of you guys might see that as me being evil, but you got a textbook that tells you what they are. So the mean for a continuous probability distribution, hopefully this kind of makes sense. I mean, if I have a continuous uniform, let me make it even more specific, uniform probability. If I had a uniform probability going from 0 to 6, what's the average? They're all equally weighted. 3, yeah. It's just the average of the two on the outside. So right in the middle. They're all equally weighted. So it's exactly like I was just talking a minute ago about the XP of X. They're all equally weighted, so the average is going to be right in the middle. So the average will be what they call A plus B over 2, where they say A is the smallest, B is the biggest. Just the average of the range that it's defined over. Let that make complete sense. Now the one that I showed to my class last semester, and they got really intrigued, and I had to bring into them the proof of it. Let's see if any of you guys want to do that. Might as well write it like this. Is this guy. The standard deviation for uniform probability is the square root of b minus a squared over 12. And I love how they were only fascinated by the fact that it was the number 12. Like, why 12? So if you want me to, I could actually print out the same thing I brought to them and show you. It kind of relies on some calculus and some other things. So I could certainly do that. So those are the two. So for the homework, you just have to plug and chuck. If the uniform distribution went from 11 to 28, you put 28 in for B, 11 in for A, and you could figure out the mean and the standard deviation very quickly. Decent little formulas. How we doing there? I'm just not going to make a big deal of it because they're not really used that much. But in the homework, I want you to realize that they exist. Okay. Anything else from homework stuff? Okay, that was good. I like that. Some questions. I appreciate it. So let me see. I think last time we did this, it really, last time was not the best one to miss if you missed out on last time. Because we did this worksheet. So does everybody have that worksheet with them? Because we're going to do the other side today. So we got this bad boy here? Okay. So this was my attempt to bridge the gap between the probabilities we were doing before into the z-score kind of thing, the normal distribution stuff. And the real point from it is, if the probability, if I draw it out of distribution and I make the area equal to 1, the total area is 1, any subset of it will just be equal to the area of that chunk, right? Just like with the uniform probability. So if I had a normal distribution, a certain mean and a certain standard deviation, that part doesn't really matter. And I want to know what the probability is that I got from this to this. Let's say this is a test. Probably that a student got some average, some score on the test higher than the average, some range of scores higher than the average. It's just going to equal the area of that. Now, uniform distributions, we have rectangles. They're beautiful. I love it. This sucker, we got a freaking rectangle with a caved in side. What the shit? I don't have an area formula for that. All right, some of you guys, if you've taken calculus, you understand that, like I said before, one big thing it does is shows you how to get the area of any shape, given how the top kind of looks, right? So thankfully, I'm not going to teach calculus to you, right? I've got the little table of values I said I'd bring. We're going to stand on the backs of other people that had computers crank them out for us, right? So I can figure out all the probabilities. So the very first thing I want to do with this sheet, and let me give us, well, let's see. Let's start off with just regular z-score stuff. Wee-ha! So remind me of a couple things. What's the z-score formula? Who remembers that sucker?
X minus u over.
Yeah.
Standard.
Cool. I love it. I like it. And if you want to think about it like a different formula, if it was a sample, it would be this. We're going to have a few more iterations of the z-score formula, because z-scores pretty much rule a huge chunk of undergrad statistics. Z-scores are the big players. We're going to have more formulas for z-score, but my assertion is they're all the same damn formula. They're all your data point minus the middle divided by the spread. Well, what's the middle? Depends on what kind of distribution we're talking about. What's the spread? Again. So we'll see different formulas. Some of them are going to be huge formulas, and I'm going to try to show you that it's the same damn formula. All of them. You can believe me or not, doesn't really matter, as long as you can use it. So tell me, whatever the mean is, what's the z-score for the mean going to be? We've done this before. What would the z-score for the mean be? And again, what's the z-score tell you? What's the z-score tell you? The distance from the mean to a data point in standard deviations, right? Or how many standard deviations from the mean to that data point. Is that cool? That's what it tells you. So what would the z-score be for the mean? How far from the mean is the mean? 0. So it's always going to be 0 right there if it's a z-score distribution I'm looking at. This would be what's called a standard normal. Yeah, there. Distribution. What that means is I've changed all the scores into z-scores. I've standardized it. So one step up would be 1, one step down would be -1, whatever the standard deviation is. Now we talked last time about this idea of the empirical rule. And it tells me what percentage I could see within so many steps of the mean if I know it's normally distributed. So who remembers what percentage was right in the middle? 95 is in 2. 68% was within 1. I like it. So tell me, what percentage then would be down here? We can use the fact that the normal distribution is symmetric. So if there's 68% inside, there's how much outside? 32. So there's how much on that side? 16. Symmetric, so I can cut it in half around the mean. So if I have a chart on which, when I look up a certain z-score, it tells me the area below that z-score. Let me say that again. If I have a chart on which, when I look up a certain z-score, it tells me the area below that z-score. And not just for -3, -2, -1, but for -1.11, -4.67, -2.39, positive 0.27, out to 2 decimal places. It better freaking tell me when I look at -1, it better be something around 16%. Or I can chuck the whole thing and do something else, right? Okay. So let me give you this guy here. We're going to talk about how to read this thing. We're going to do several problems together. And I desperately want you to understand, the reason we're moving in this direction is because there are a lot of things in the world that are normally distributed. In fact, that's sort of where the word came from. So like heights of people. Men, women, when you combine them, it gets a little bit freaky. But men, women, normally distributed. Most people will be near the average, very few out here. Right? So if I just had a way to figure out the probabilities quickly, I could figure out how tall to make a door. I could figure out, how much clearance I need. I could figure out how many people are going to hit their head if they don't realize some bar is coming, and if I should put a warning or not to cover my ass legally, stuff like that. You guys with me? Because I'll be able to answer questions about, if I know it's normally distributed, I'll be able to answer questions like how many people are below this height, given a certain number of people. What percentage are there? And then if I have 500 people coming, how many of them would I expect to be less than that height? Well, I expect to be 16% of them would be less than whatever that height is. Because I know it's normally distributed. Let me give this to you. Should have sent a poet. Alright. So, sort of like trying to figure out how to read a map or something. It's got weird ass sectors and shit. We got to figure out how to read this. Now, they could have done different ways, but then it would have been much bigger and grosser, to be honest. So there's a negative side and a positive side. So z-scores obviously can be negative. That would just mean that they are below the mean. Right, so you don't want a negative z-score on a test or something. That would suck. We got below average. So let's see how to read this. And the first thing I want to read off of this is related to this. 16% you're supposed to get. So the way to read this takes a little bit of getting used to. But what do I want to look up then? Out to 2 decimal places, I want to look up -1.00. Right? So notice how this the rows tell you out to the first decimal place, and the columns tell you what that second decimal place would be. So if I want negative 1.00, I would go to negative 1.0. Oops, so I needed a negative sign. Negative 1.0. So I get 0.1587, which if I round it, is 16 freaking percent, right? I mean, that's... So I can find the empirical rule in this. So what I call this sometimes is this is the empirical rule on steroids. This is like, I can see not just 1, 2, 3 steps, I can see all these steps in between. Because somebody's height doesn't have to be exactly 1 or 2 or 3 steps up. It could be 0.73 steps up. It's like, holy shit, how do I get that probability of that happening? So now we can't. So what about, can you guys look this up then? What would the area be? So this, you'll hear me say several ways. That the area of this is 16%, which means the probability that a z-score is in here is 16%, which means that 16% of the z-scores would occur in there, right? So area is the same thing as percentage. It's the same thing as probability. So you'll hear me say it. I won't even think about it. I'll just say it several different ways. So what area is there below 1.17? And notice, again, I said this earlier, but just to really show you. Whenever you look up a z-score on this chart, this very single-minded chart will always tell you the area below it. So we're going to have to figure out what the hell do we do if I want an area above something? What the hell do I do if I want an area between two things? Oh, shit. So what is the area below 1.17 z-score? So if I look up 1.17, yeah, I get 0.8790. So is it? Okay, if I round up, an 88% chance of that, something happening in that region. Which makes sense, because what area is below 0? 0 cuts it in half, so 50%. So as I move up this way, that's why the numbers get larger and larger. Because as I move up, I'm getting more and more stuff below me, right? Okay, I like it, I like it. All right, so let that make sense. So using the chart, I know it feels old school. I don't even know if you guys realize that we used to use log tables to figure out log of 11. Hopefully everyone here knows what I mean when I say log, and I'm not talking about wood. All right. But I still believe in using the chart because you just get a feel for what happens as you move around in here much better than you would just by pushing a damn button. And again, if you push a damn button and get the answer and that's all you did, you're not going to get any points for that. Your calculator will pass and go to the next level. So here, let's try a few more. Let me see what you guys think about this here. What would the probability of a z-score bigger than negative 2.12? And here's something I highly recommend. I'm not going to make it necessary, but if you don't do this and you make a mistake, you're going to lose more points because you're not doing what you should for yourself. You should draw the picture and shade in the area that we want. It'll be kind of a check to make sure that it makes sense. So what would this look? Where would negative 2.12? Here's another thing that makes me a little crazy. People just kind of put this wherever they want to. What's in the middle? It's got to be 0 because it's the mean, and the mean becomes 0. So don't put negative 2.12 up here, please. It doesn't have to be perfect. Don't get me wrong. Maybe not right here. Somewhere over there. That's beautiful. Negative 2.12. Should be a couple steps down. Notice about that. And what's the area that I want? No. I mean, where on the picture? Sorry. Yeah, well, greater than, so it's going to be this way. Go with me. So what do you get when you look up negative 2.12?
.0170.
Yeah, 212, I get 0.0170, but where does that go in the picture? The minute I use the z-score to get something, I know it's got to go below the z-score. That's what it tells me. The area below this is 0.0170. So how do I get the area above it? Yeah, the whole thing is 1. So this side has got to be 1 minus this. Yeah. So what makes this 9? 9. What makes this 9? 8. What makes this 10? 3. 9, 8. Or, you know, do it in your calculator. Sure. I have hope for us as humans, so I do. So that's the first little adjustment we have to make. Since the chart is very single-minded, we might have to adjust the number we get from it. And that's the most basic adjustment is, I want what's above it. Now, I'm going to say the next thing once. If you understand it fully, use it. If you don't understand it, who cares? It doesn't save you that much time. But because this is symmetric, if I look up, what do you get when you look up positive 2.12? .983. Now, if you think about it, it's because it's symmetric. The area that's below, that would be above this, is the same as the area that would be below positive 212. If you understand that and you know when you can do that, do it. If you're not 100% certain about one of those two things, never do it. It's sort of like if you forget to turn off your blinker, just don't use it. Don't be going this way when your blinker's going that way. Old man Jeff. You guys understand that? So if you understand the shortcut, beautiful. It's a little shortcut. It'll help you out a little tiny bit. If you don't, it's not going to kill you. Okay, so what about another adjustment that we have to make? And then we'll talk about backwards problems, right? I think I can turn some lights back on. All right, cool. What if I want the area between two z-scores? If we kind of give ourselves, and you don't have to make a perfect normal distribution. In fact, I had a student that would do it like this, a little pyramid. Who gives a shit? It's just a quick visual anchor, sketch, to kind of see where things are, make sure your answer makes sense, understand what to do mathematically with the numbers you get. I don't care, just make it symmetric at least, with the highest point in the middle. So maybe try to do better than that. So here's 0 again. Here's 0.17. And there's 1.53. All that really matters is that they're relatively in the right place. It doesn't matter if they're exactly scale, who cares? It's just a quick visual sketch. I'm not sure what a non-visual sketch would be, what real we are. So there's the area I want, right? Now, some of you guys might have an idea what to do with this mathematic, how to get exactly that. The chart doesn't tell me this worth shit. It only tells me areas below z-score. So if I looked up 1.53, what do you get when you look up 1.53? Yeah, 937, right? 0.937, is that cool? Is that too much or not enough area? Too much freaking area, because I should have stopped where? I don't want to go forever. I should have stopped right here. So if I take this area and I subtract it, I'll end up with the area in the middle. That makes physical sense. All right? You cut this board too long. Let me subtract some off. No, there you go. So what do you get when you look up 0.17? 5675? Please let me know now if you have any trouble with that chart. You gotta let me know, because that chart, by the way, I should have said this sooner, but You're going to be using that sucker on tests and quizzes and stuff. And you're going to turn it in. Don't write on it. You can put your name on it. That's perfect. But don't put any notes on that sucker, right? I will bring some clean ones with me just in case you forgot that. But if you turn it in, there's some notes on it, you're going to lose points for that because other people don't have it. And then all you got to do here is subtract these two. Maybe. 3695. Yes? I like it. I like it. Now, I understand. Please, dear God. Please understand. We haven't done any physical real-world problem yet. We're just investigating how to look at this. But I know how to convert real-world measurements into z-scores. And once they are z-scores, and if I know it's normally distributed, I can use the hell out of this thing to get all the probability answers I want. So a big chunk of like introductory statistics is to say, well, am I dealing with a normal distribution or not? Because if I am, sweet, I got all the answers just waiting for me. If I'm not, shit, I got to do some weird statistics 2 stuff if we only offered statistics 2. Okay, maybe. All right, so, let's do a backwards problem because mathematics doesn't care which way you want it to go. You can go both ways, right? Think of it what you will. So if I said, let me just give you a visual of this and then we'll try some real problems out here. If I said what z-score has an area of, what you got, Joe? 0.1190. I don't know if that's on there, but we'll see. See if you can figure out how to answer this. Is the z-score chart perfect in resolution? No, it only goes out 2 places on the z-score, right? So your answer is going to involve what's the closest. The most important thing to realize right now is this ain't a z-score, right? Don't be trying to look up 0.12 in a z-score. The question is, what is a z-score? This is the area, and where are areas on the chart in the body, right? So if I look at, hopefully it becomes obvious, it's going to be a negative.
It's negative 1.18. Exactly.
Yeah, so I get, that's good, Jeff. So if I look at negative, so if I look at 0.1190, the closest I can get.
It's exactly.
Oh, is it?
0.18.
I thought it was on there.
Yeah.
That's a little scary for me. Been teaching stats so long, I remember these numbers. Holy shit. 0.1190 exactly lines up with what z-score? Negative 1.18. You guys see how to see it? So you find a z-score, and you look back out to see what, find the area, you look back out to find the z-score. So if you can look a z-score up and find an area, you have to be able to do that backwards. I like it. So negative 1.1, forgot. 8, is that right? Yeah. So what about, here, you'll love this question. Find the z-score for P, what do you got, Jeff? Let's do P79. Sure. I love it. I love that reaction. You got to remember what the hell that symbol means. What's P sub 79 mean? The 79 percentile, which means it would be the z-score that has 79% below it. Holy shit, that matches up exactly with what the hell we're talking about. So can you find a z-score that would be the 79th percentile? Some of you guys might realize, same damn question we just did, just a different area. Where's it going to be? Is it going to be positive or negative? It's got to be positive. It's got to be above the mean, because the mean would have 50% below it. This sucker's got 79% below it. I don't know yet. Haven't even looked at it. So here's the right way. So P79. So I know it's going to be up here somewhere, because that's 50%. So the first thing is to realize How do you know where it is? Well, you just figure out based on what the probability is. I know it's 79%, so it must be above the mean. This is 0.79. So the biggest mistake you guys might realize is that probabilities look like z-scores. That's evil. So people just look up 0.79 z-score and they'll go, oh, that's the number, okay. Doesn't make any sense. It's the z-score that I don't know. It's the percentage I know. So if you look at 0.79, what's the closest you can get to 0.79?
0.81.
Yeah, let's see, 79. 0.81, I agree. Look at the other option, 0.7881. Do you see what I mean when I say that's 19 away? 7881 is 19 away from 0.79. 0.7910 is only 10 away. Now when I took stats, we actually had to do what's called interpolation and figure out the z-score in the middle of those that matched up with how far off it. Oh, screw that. Screw it. So yeah, this will be, what did I just say? Thank you, 0.81. So once you go up about 0.8 of a step, just about, and just a little bit more, you've got 79% of it below you. I love it. Okay, I like it. So I want you to realize this one piece of paper will work for men's heights. It'll work for fish lengths if they are normally distributed. It'll work for most things like heights and lengths and things that deal with things growing, because most things will grow to a certain height for a given species of tree. There's like a certain area where you would expect it, and then you're like, well, that's a really tall, that kind of tree. If you knew trees, which I don't. Right, that's really tall for that. That's a really short tree. Or that's a really tall human. That's a short human. Right? It's a weird way to say that. I don't care. So here's what I want you to do. Some of you guys might have already started doing this, but on the reverse side of that binomial dude with the little gray pyramid in there, start working on number 1. And I love that I made the next number 4. But start working on number 1 there. Please, dear God, if you want to, we can work together. If you don't have any calculator at all, I do have some scientific calculators. You need to borrow one of those. Actually, you don't need any calculators for the first one, sorry. It'll be number 4 that we need a calculator for. Okay. I'll get an idea. Thank you.
0.79.